We continue our lecture on sequences and their convergence. Of course, you are familiar with the squeeze theorem from your previous calculus course, and we will use the same concept in evaluating limits of sequences. We have the following theorem. Let the set containing a sub n's, b sub n's, and c sub n's be sequences. If b sub n is greater than or equal to a sub n and less than or equal to c sub n, for all n greater than or equal to k, for some non-negative integer k, and the limit of a sub n and the limit of c sub n as n goes to infinity are both equal to L for some real value L, then the limit of b sub n as n goes to infinity will also be equal to L. We have the graph shown below. So in this graph, the blue, green, and red dots represent the terms of the sequences of a sub n, b sub n, and c sub n, respectively. Observe that for values of n greater than or equal to k, here, the green dots are always between the red and blue dots for the same value of n, and we can show, and if we can show that the limit of the red and blue dots are equal, then the green dots will be forced to have the same limit. So if the blue dots and the red dots both approach the same value, then the green dots will be forced to approach that same value L. In this example, we determine whether the sequence of n factorial over n raised to n, with n ranging from 1 to infinity, is convergent or divergent. Note that f of x equal to x factorial over x raised to x is not defined for non-integer values of x, which means evaluating the limit of this function will not be straightforward. So instead, we will use the squeeze theorem to solve this problem. So first, we define a sub n equal to n factorial over n raised to n. And note that for each n greater than or equal to 1, we have a sub n greater than 0. This is true since n factorial is always positive, and n raised to n will also be positive. Now, we can write this as the product 1 times 2 times 3 times and so on up to n, all over the product n times etc. up to n, where we have n factors of n in the denominator. And we can split this into n fractions in the following manner. We have 1 over n times 2 over n times 3 over n, and so on up to n over n. Now, what do we observe here? These fractions here are all less than or equal to 1. Okay? Which means this product is less than or equal to 1 over n times 1 times 1 times etc. And this can be simplified as 1 over n. So observe that a sub n is greater than 0 and less than or equal to 1 over n, which means if we find the limit of this expression as n goes to infinity, we have 0 as the limit. And if we find the limit of this expression as n goes to infinity, since the denominator goes to infinity, this fraction goes to 0. Hence, it follows from the squeeze theorem that the limit of a sub n, or the limit of n factorial over n raised to n as n goes to infinity, will also be equal to 0. Therefore, the sequence containing the terms n factorial over n raised to n with n ranging from 1 to infinity is convergent, and its limit is 0. However, we must remember to use the squeeze theorem carefully. We must select terms whose limits as n goes to infinity are equal. Otherwise, the squeeze theorem cannot be applied using those terms. In this next example, let's determine whether the sequence of terms -1 raised to n over n, with n ranging from 1 to infinity, converges or diverges. If we want to use the squeeze theorem, we must find two terms we can use to sandwich the terms of our sequence. So for each n greater than or equal to 1, -1 raised to n is either -1 or +1, which means -1 raised to n all over n is between -1 over n and 1 over n. Now, let's evaluate the limit of these terms here. Note that the limit of -1 raised to n as n goes to infinity is equal to 0, and the same can be said about the limit of 1 over n as n goes to infinity. Since both these terms approach 0 as n goes to infinity, it follows from the squeeze theorem that the limit of -1 raised to n over n as n goes to infinity will also be equal to 0. Next, we define some properties of sequences which will be useful in determining their convergence using some theorems later on. So a sequence of a sub n is said to be the following if these conditions are satisfied. So number 1, it is said to be constant if a sub n is equal to a sub n plus 1 for all values of n. In other words, all the terms in this sequence are equal. Second, it is said to be increasing if a sub n is less than or equal to a sub n plus 1 for all values of n. It is said to be decreasing if a sub n is greater than or equal to a sub n plus 1 for all values of n. And it is said to be monotone if it is either increasing or decreasing. Also, a sequence is said to be strictly increasing if a sub n is less than a sub n plus 1 for all n greater than or equal to k. In other words, the consecutive terms are strictly increasing if the next term is strictly greater than the previous term. Similarly, a sequence is said to be strictly decreasing if a sub n is greater than a sub n plus 1 for all n greater than or equal to k. Now, a sequence is said to be ultimately increasing if the sequence is increasing for some values of n, for some value of m greater than or equal to k. Respectively, it is ultimately decreasing if the sequence is decreasing for some value of m greater than or equal to k. In other words, we can say that a sequence is ultimately increasing if we can get a tail end of that sequence, and that tail end is an increasing sequence. And the same can be said about an ultimately decreasing sequence. Now, the following remark gives us ways of showing that a given sequence is increasing. A sequence is increasing if, number 1, a sub n plus 1 minus a sub n is greater than or equal to 0 for all values of n greater than or equal to k. In other words, the difference between the consecutive terms is non-negative. Second, we have a sub n plus 1 over a sub n is greater than or equal to 1 for all n greater than or equal to k, given that the denominator is positive for all n greater than or equal to k. In other words, the ratio of consecutive terms is greater than or equal to 1. Third, if the derivative of f is non-negative for all values of x greater than or equal to k, given that a sub n is equal to f of n for all non-negative integers n, where f is differentiable on the interval k to infinity. Analogous conditions can be obtained which imply that a sequence is strictly increasing, decreasing, or strictly decreasing. Now, for this example, let's determine whether the sequence containing the terms e sub e raised to n over n, with n ranging from 1 to infinity, is increasing or decreasing. So first, we define f of x equal to e to the x over x, which we know to be differentiable on the interval 1 to infinity. Getting its derivative using the quotient rule, we have f prime of x equal to x times e to the x minus e to the x all over x squared. And factoring e to the x gives us the following. We have e to the x times the quantity x minus 1 all over x squared. Now, we know that this is greater than or equal to 0 for all values of x greater than or equal to 1, since e to the x is non-negative, while x squared is always positive. And since x is greater than or equal to 1, we also know that this factor is greater than or equal to 0. Thus, f is increasing on the interval 1 to infinity, and so the sequence is also increasing. In this next example, we determine whether the sequence of terms 2 raised to n over n factorial, with n ranging from 2 to infinity, is increasing or decreasing. So let's first define a sub n as 2 raised to n over n factorial. Then for all n greater than or equal to 2, the difference between the consecutive terms is given by 2 raised to n plus 1 over n plus 1 factorial minus 2 raised to n over n factorial. What we can do here is we can combine into a single fraction. The LCD will be n plus 1 factorial, and the numerator will become 2 raised to n plus 1 minus 2 raised to n times n plus 1. Now, factoring out 2 raised to n will give us the following. We have 2 raised to n times the quantity 1 minus n all over n plus 1 factorial. And we know that this is less than 0 since we know that 2 raised to n is non-negative, n plus 1 factorial is non-negative, while 1 minus n is less than 0. This tells us that the given sequence is decreasing, or if we want to be more specific, we can say that it is strictly decreasing. Alternatively, since a sub n is greater than 0 for all values of n, we can take the ratio of the consecutive terms. We have the following. We have 2 raised to n plus 1 over n plus 1 factorial all over 2 raised to n over n factorial. And we can write this in the following manner. And simplifying this, canceling the common factors, will give us 2 over n plus 1. And we know that 2 over n plus 1 is less than 1 since n is greater than or equal to 2. The denominator will always be greater than the numerator, which means this fraction is strictly less than 1. Hence, we have the same conclusion. For our next definition, we describe what it means for a sequence to be bounded. A sequence of a sub n is said to be first bounded below if there exists a real number m such that a sub n is greater than or equal to m for all values of n. And the number m here is called a lower bound for the sequence. Second, it is bounded above if there exists a real number capital M such that a sub n is less than or equal to capital M for all values of n. and this number capital M is called an upper bound for the sequence. And third, a sequence is said to be bounded if it is both bounded below and bounded above. Now, for example 9, we want to show that the sequence containing the terms -1 raised to n over n, with n ranging from 1 to infinity, is bounded. Note that for each n greater than or equal to 1, we have the following inequality. -1 raised to n over n is between -1 and +1. This is true since 1 over n is positive and less than or equal to 1, and multiplying -1 raised to n to it yields this inequality. Therefore, the sequence is bounded below by -1 and bounded above by 1. Hence, the sequence is bounded. Now, an increasing sequence is bounded below by its first term, and a decreasing sequence is bounded above by its first term. The proof for these remarks will be left as an exercise for the viewer. For our next example, we want to show that the sequence of 2 raised to n over n factorial, with n ranging from 2 to infinity, is bounded. Note that the terms of the sequence are always positive, so that the sequence is bounded below by 0. Also, it was shown in example 8 that the sequence is decreasing. Hence, by item 2 of the above remark, the sequence is bounded above by its first term, which is equal to 2. Hence, the sequence is bounded. Now, this next theorem uses the previous sets of definitions that we discussed earlier. So we have the monotone convergence theorem. And this theorem tells us that if a sequence is bounded and monotone, then it is convergent. Or equivalently, a monotone sequence is convergent if and only if it is bounded. This theorem is useful in showing convergence of sequences without explicitly showing that the limit of its terms as n goes to infinity exists, or without explicitly evaluating the limit. For example, let's show that the sequence of 2 raised to n over n factorial, with n ranging from 2 to infinity, is convergent. First, evaluating the limit of this sequence is not straightforward. However, if we want to use the monotone convergence theorem, we just need to show that this sequence is monotone and bounded. Note that it was shown in example 8 that the sequence is decreasing, hence it is monotone. Furthermore, the sequence is bounded as proved in example 10. Therefore, by the monotone convergence theorem, the sequence is convergent. So as you can observe here, we have shown that a sequence is convergent without explicitly solving for its limit. Now, to get a better understanding of today's lecture, please answer these exercise items. And if you have questions regarding today's lecture, please do not hesitate to contact your Math 22 instructor. Have a good day.